On October 23, 1943, inside a maintenance hangar at Erprobungsstelle Rechlin, the Luftwaffe's main flight testing center, 70 miles north of Berlin, 3 engine specialists stood around a Wright Cyclone radial engine that had just been removed from a captured Boeing B-17 Flying Fortress. 2 weeks earlier, this bomber had been sitting in a muddy clearing near Varda, Denmark. A forced landing. The American crew had bailed out. The pilot had brought her down on soft ground, and the soft ground had saved the aircraft. Barely a scratch. Hans Werner Lerche, 29, Rechlin's chief evaluation pilot, had personally flown the bomber out of that field, nursing it on 3 engines to Esbjerg Airfield, then on to Rechlin. He'd already noted something in the cockpit that unsettled him. The instruments were color-coded. The controls were intuitive. The turret mechanisms were simpler than anything he'd seen on a German bomber. But Lerche was a pilot. What the engine men were about to find was something else entirely. The cowling came off. 9 cylinders arranged in a star pattern, each one finned for air cooling. A Wright R1820 Cyclone, 1,200 horsepower. The German engineers had seen radial engines before. They built the BMW 801, a fine engine, a powerful engine. They expected to find something crude. American mass production, sloppy tolerances, corners cut for speed. What they found was the opposite. The cylinder heads were uniform, not close to uniform, identical. The machining on the crankcase was clean, precise, consistent. There were no file marks. No evidence of hand fitting. No shims wedged into gaps where tolerances hadn't quite met. Every bolt, every gasket seat, every rocker arm looked as though it had been made by the same hand on the same afternoon. Then, one of the engineers checked the data plate riveted to the engine housing. And here is where this story changes direction. Because the plate did not say Wright Aeronautical Corporation. It said Studebaker. Studebaker Corporation, South Bend, Indiana. A car company. A company that made sedans and pickup trucks had built this aircraft engine and built it to a standard that matched or exceeded anything coming out of BMW's facilities in Munich. If this channel has earned your trust, a like and subscribe helps these stories reach the people who'll care about them most. Remember that data plate. Because what it meant was not what the engineers assumed that morning. They assumed it was a curiosity, an oddity of American logistics. A car company pressed into wartime service, producing a few hundred engines under supervision from the real manufacturer. That would make sense. That would fit inside the world they understood. But the number stamped next to the Studebaker name was a production serial. And that serial number was high. Very high. By October 1943, Studebaker had already produced tens of thousands of these engines across 3 new factories, South Bend, Fort Wayne, Chicago, employing 9,400 workers who, 2 years earlier, had been building passenger cars. This was not a curiosity. This was a system. And the engine in front of them was not a prototype, not a hand-built showcase sent to impress. It was one of thousands. One of tens of thousands. Mass-produced by people who had never built an aircraft engine before 1941. And every single part fit every other part, without a file, without a shim, without a master craftsman leaning over the assembly bench. The Germans at Rechlin were among the best engineers in the Luftwaffe. They understood engines the way a surgeon understands anatomy. And they understood, standing around that Wright Cyclone on that October morning, that they were looking at something their country could not replicate. Not because the engine was more advanced. Not because the metallurgy was superior. Not because American engineers were smarter than German engineers. But because of something else. Something embedded in the way every part mated to every other part without human intervention. Something in the system that produced it. Something that had no equivalent in the German war machine. What that something was and why it would prove more devastating to Germany than any single weapon the Americans ever built begins not in that hangar in Rechlin, but 6,000 miles away, in a factory that still smelled of car paint. To understand what those engineers were looking at, you first have to understand what they were used to. In the autumn of 1943, the Luftwaffe's primary radial engine was the BMW 801, a 14-cylinder, air-cooled power plant that produced roughly 1,600 horsepower. It was a good engine, in some ways a brilliant engine. It featured a device called the Kommandogerät, an analog computer built into the cowling that automatically managed propeller pitch, fuel mixture, ignition timing, and supercharger boost with a single throttle lever. German engineers were justifiably proud of it, but building one was a different matter. At BMW's main aero engine plant at Allach, outside Munich, a finished 801 was not so much manufactured as composed. Skilled technicians, Facharbeiter, assembled each engine by hand, selecting parts, checking tolerances with calipers and micrometers, filing down a bearing housing that ran 0.03 of a millimeter too wide, shimming a crankcase joint that didn't quite seat. The work required years of training. A master engine fitter at Allach could feel a misalignment with his fingertips that a gauge might miss. His hands were the final quality control. This was not inefficiency. This was tradition. German engineering culture, stretching back to the guild system of the Middle Ages, believed that precision came from the craftsman, not from the machine. The machine cut the rough shape. The man made it perfect. Every BMW 801 that left Allach was, in a meaningful sense, unique. Its parts belonged to it, and to no other engine. Cylinder number 4 from engine number 6000 would not fit into engine number 6001 without adjustment. It might not fit at all. Now hold that thought, because here is what that tradition looked like at 20,000 feet over France in the winter of 1943. A Focke-Wulf 190 takes a 50 caliber round through the cowling. The bullet doesn't kill the engine. It cracks a rocker arm cover on cylinder number 7. Oil begins to seep. The pilot nurses the aircraft back to his field in Belgium. The ground crew opens the cowling, identifies the damage, and calls for a replacement cover. The part arrives 3 days later from a depot near Frankfurt. It is the correct part number. It is for a BMW 801, but it was manufactured at a different facility during a different production run. The mechanic holds it against the engine and it does not seat properly. The bolt holes are off by less than a millimeter. He reaches for his file. 45 minutes later, the cover fits. The mechanic is good at his job. He has done this before. Every mechanic in the Luftwaffe has done this before. Hand-fitting a replacement part is not a failure of the system. It is the system, and nobody questioned it because nobody had seen the alternative. That alternative was sitting in a hangar at Rechlin under fluorescent lights, with its cowling panels leaning against the wall and a data plate that read Studebaker Corporation. What made that engine different was not power. The Wright Cyclone produced 1,200 horsepower. The BMW 801 produced 1,600. On paper, the German engine was superior. What made it different was not sophistication. The Kommandogerät was more advanced than anything in the Cyclone's design. What made it different was not even build quality. The Allach craftsmen were among the finest machinists in the world. What made it different was a single radical idea that American industry had been refining for over 100 years. An idea so deeply embedded in the way Americans built things that no engineer in South Bend would have thought to mention it, the way a fish doesn't mention water. The idea was this: no human hand should ever need to touch a part to make it fit. Every component of that Wright Cyclone, every piston, every valve spring, every rocker arm, every one of the roughly 8,000 individual pieces was machined to a tolerance so precise that any part from any engine built in any factory on any day, could be dropped into any other engine of the same model, and it would seat, seal, and function without adjustment. The Germans had a word for their way of building: Meisterwerk, masterwork, the product of a master's hands. The Americans had a word for theirs, too. They had been using it since 1801, when a gunsmith from Connecticut walked into a government office with a bag of musket parts and assembled 10 working firearms from a pile of pieces chosen at random. They called it interchangeability, and what it meant for the air war over Europe, what it meant for every Luftwaffe pilot climbing into a cockpit, every German mechanic filing down a replacement part, every factory in the Reich running 3 shifts with fewer skilled hands every month, was something the engineers at Rechlin were only beginning to grasp. Because interchangeability didn't just change how you built an engine, it changed who could build one. In January of 1941, a delegation of engineers from the United States Army Air Corps arrived at the Studebaker Corporation's main plant in South Bend, Indiana, carrying blueprints for the Wright R-1820 Cyclone radial engine. They asked a question that, in Germany, would have sounded absurd. Can you build this? Studebaker had never built an aircraft engine. Its workers made sedans, Champions and Commanders, solid, mid-priced cars for American families. The factory floor smelled of paint and upholstery glue, not aviation fuel. The machinists who ran the lathes had never held an aircraft piston in their lives. But the Army wasn't asking Studebaker whether its workers understood radial engines. The Army was asking whether Studebaker understood tolerances, whether its machines could hold dimensions to within a few 10,000ths of an inch, hour after hour, shift after shift, part after part, without drift. Whether its quality control systems could catch a defect before it left the floor. The answer was yes, because that was what making cars in America required. Here is a detail worth keeping in your mind, because it will come back. By 1941, American automobile manufacturers had spent 3 decades refining a production philosophy that treated the human hand as a source of error, not precision. Every part was designed to be made by a machine and checked by a gauge, not felt by a fingertip. The skill lived in the tooling, not in the man. A new worker could be trained in weeks, not years, because the machine enforced the standard. The worker fed it material, monitored its output, and pulled the defective pieces. The machine did the rest. Within 18 months, Studebaker had 3 new factories running: South Bend, Fort Wayne, Chicago. 9,400 workers on the floor. And the engines they produced were indistinguishable from those built by Wright Aeronautical itself, because they were made from the same drawings, to the same tolerances, using the same gauging system. A piston machined in Fort Wayne dropped into a crankcase bored in South Bend, and it fit. No file, no shim, no master craftsman required. Now come back to Rechlin. In the weeks following that first examination, the German engineers did not simply look at the captured Wright Cyclone. They dismantled it completely. Every cylinder pulled from the crankcase, every valve removed from its guide, every bearing measured, weighed, cataloged. They laid 8,000 parts across a workshop floor in careful rows, the way a surgeon lays out instruments, and they began to compare. What they found was methodical and relentless. The bore of each cylinder was identical to every other cylinder, not close, not approximately, but within machining tolerances so tight that the variation between the widest and the narrowest was less than the thickness of a human hair. The valve seats showed the same consistency. The connecting rods, the push rods, the rocker arms, all interchangeable, all seated without intervention. But the engineers did something else, too. Something that turned a technical finding into a strategic one. They had access to parts recovered from B-17 wrecks across occupied Europe, crashed bombers whose engines had been shattered, burned, or half buried in French farmland. They took components from those wrecks and tried to install them into the intact Cyclone on their bench. They fit. A rocker arm pulled from a burned-out engine that had crashed near Abbeville slid into the guide of the Recklin engine as though it had been made for it. Because it had been. Not made for this specific engine. Made to a specification so exact that it belonged to every engine of its type, regardless of which factory had produced it, regardless of which week, regardless of which worker had been standing at the lathe. Think about what that means from the perspective of a Luftwaffe maintenance officer in France. When an American bomber was damaged, its ground crew didn't need the right part from the right factory. They needed any part with the right number. Any crate from any depot, from any shipment that had crossed the Atlantic on any convoy. The part would fit. The bomber would fly again. Tomorrow. When a German fighter was damaged, its ground crew needed the specific part, and if that part had been made at a different facility, or during a different production run, a mechanic with years of training had to modify it by hand. If no such mechanic was available, the aircraft sat. And by the autumn of 1943, such mechanics were becoming very hard to find, because the war was swallowing them. By October of that year, BMW's Allach plant had begun replacing its trained Facharbeiter, the master fitters, the men whose hands made the system work, with forced laborers, prisoners, foreign workers conscripted from occupied territories, men and women who had never seen an aircraft engine, who did not speak German, who worked 12-hour shifts under guard. By the end of 1944, more than 29,000 forced laborers would make up over half of BMW's entire workforce. And here is the thing that no one in the German system wanted to say out loud. The forced laborers could not do what the Facharbeiter did. They could not feel a misalignment with their fingertips. They could not judge a tolerance by sound. The quality coming off the line at Allach was declining, not because the design had changed, but because the hands had changed. The entire German production model depended on skilled human beings, and the war was taking those human beings away. The American model depended on machines, and machines did not get drafted. That was the first layer of what the engineers at Rechlin had uncovered, but there was a second, and it was worse. Because interchangeability did not merely make repair easier, it did something far more dangerous to Germany's position in the air war. It made production scalable. And what scalable production looked like, in American hands, was something the Luftwaffe had never had to face before. In Dearborn, Michigan, in the spring of 1942, a foreman at the Ford Motor Company's Rouge plant stood watching a row of women, most of them under 30, most of them hired in the last 6 weeks, assembling 18-cylinder Pratt & Whitney R2800 double WASP engines. These were the engines that powered the Republic P-47 Thunderbolt, the heaviest single-engine fighter in the world. 2,000 horsepower, 18 cylinders in 2 staggered rows of 9, a machine of extraordinary complexity. The women had been making car parts 4 months earlier. They were not engineers, they were not machinists in the German sense. They had no years of apprenticeship, no guild tradition, no master's eye for fit and finish. What they had were jigs, fixtures, gauges, and a process so precisely engineered that every step was designed to be performed correctly by someone who had never performed it before. The skill was in the system. The worker was the system's hands. Ford's Rouge plant would eventually produce 57,851 R2800 engines during the war. At the start, it took 2,300 hours of labor to build one. By the end of 1944, it took 1,028. Not because the workers had become master craftsmen, because the process had been refined. Tooling adjusted, bottlenecks removed, sequences reorganized, until the factory itself was the craftsman. Now here is the number that matters. Hold it alongside everything you already know. In the entire war, Germany produced roughly 61,000 BMW 801 engines, its primary radial, the one that powered the Focke-Wulf 190. 61,000. It was a staggering achievement, especially under Allied bombing. It required the labor of tens of thousands of workers, many of them prisoners, across multiple facilities. America produced over 125,000 Pratt & Whitney R2800s alone, just that one engine type. Ford built 57,000 of them. Pratt & Whitney built the rest. And those 125,000 double wasps were just a fraction of America's total engine output, because at the same time, Studebaker was building 63,000 Wright Cyclones for the B-17, Dodge Chicago was building 18,000 Wright duplex Cyclones for the B-29, Buick was building Pratt & Whitney radials for Navy fighters, and Packard was building Rolls-Royce Merlins under license for the P-51 Mustang. Car companies. All of them. Building aircraft engines by the tens of thousands. And every single part from every single factory fit every other part from every other factory. A mechanic at an 8th Air Force base in East Anglia could pull a cylinder assembly from a crate marked Studebaker, South Bend, and install it on a B-17 whose original engines had been built by Wright in Paterson, New Jersey. It would fit. He didn't need to know where it came from. He didn't need to file anything. He needed a wrench and 30 minutes. A Luftwaffe mechanic at a field in Normandy, replacing the same type of component on a Focke-Wulf 190, needed the part, the file, the calipers, the training, and the time. And by the summer of 1944, he was running out of all 5. This is the moment to understand something about what the engineers at Rechlin had actually discovered when they opened that engine cowling. They thought they were evaluating a machine. They were evaluating a civilization. The ability to produce interchangeable precision parts at enormous scale was not something America had invented for the war. It was something America had been doing since the 19th century, since the armories at Springfield and Harper's Ferry had figured out how to make musket locks that swapped between rifles without hand-fitting. The automobile industry had taken that principle and driven it to an extreme that no other nation on Earth had matched. Henry Ford's moving assembly line, introduced in 1913, was not just a method of building cars. It was a method of encoding skill into machinery, of making the process so robust that the quality of the output did not depend on the quality of the individual worker. Germany had tried to compete with this. Albert Speer, appointed Minister of Armaments in February 1942, had pushed hard for rationalization, fewer models, longer production runs, more standardized components. He achieved real gains. German war production tripled between early 42 and mid-44, a remarkable feat under constant bombardment. But Speer could not change the fundamental architecture of German manufacturing in the middle of a war. He could build more engines. He could not make them interchangeable. The tradition was too deep. The tooling was wrong. The workforce was vanishing. And the clock was running out. And something else was happening in the skies over the Reich that made this industrial gap not merely significant, but lethal. Because the Americans were not just building more engines than Germany, they were losing them faster than Germany could shoot them down, and replacing them faster than Germany could replace its pilots. The air war had become a math problem, and the math was about to become unbearable. In the autumn of 1943, the 8th Air Force was bleeding. Over Schweinfurt, over Regensburg, over targets deep inside the Reich, the heavy bombers were being torn apart. On October 14th, the same week Lerche was pulling that B-17 out of a Danish field, 60 B-17s went down over the ball-bearing works at Schweinfurt. 60. 600 men in a single afternoon. The Luftwaffe's fighter controllers were calling their pilots home with kill tallies they hadn't seen since the Battle of Britain. In Berlin, propaganda newsreels showed burning fortresses falling in spirals, and the message was clear: America cannot sustain this. The message was wrong. By December, the 8th Air Force had more B-17s than it had lost in the entire year. Not because fewer were being shot down, because more were being built. And more were being repaired. Here is where interchangeability stopped being an engineering concept and became a weapon. At air bases across East Anglia, Thorpe Abbotts, Kimbleton, Grafton Underwood, maintenance crews worked through the nights after every major mission. A B-17 comes back with a shattered No. 3 engine, a line of holes stitched across the wing root, a feathered propeller on No. 1. In the German system, that aircraft would sit for days, waiting for matched parts, waiting for a specialist, waiting for a component that hadn't been ground down by a craftsman at the Wright factory. In the American system, the crew chief walked to the parts depot, pulled replacement assemblies off the shelf, any crate, any serial number, and installed them by morning. A ground crew of 6 enlisted men, most of them trained in 8 weeks, could swap a Wright Cyclone engine in under 4 hours. They didn't rebuild the engine in the field. They replaced it. Bolted on a new one from the crate, connected the fuel lines, the oil lines, the electrical harness, ran it up, checked the magnetos, and signed it off. The damaged engine went into a crate and shipped back to a depot, where another crew, also trained in weeks, not years, would disassemble it, replace the failed components with interchangeable parts, and send it back into the supply chain. The bomber flew the next morning. Across the channel, the Luftwaffe was fighting a mirror image war, and losing it in the hangars before losing it in the sky. By late 43, German fighter readiness rates had become a crisis that no amount of courage could solve. In some Jagdgeschwader, fewer than half the aircraft were operational on any given day. Not because they had been destroyed, because they could not be repaired fast enough. A Focke-Wulf 190 returns to its field outside Lille with a damaged cylinder on its BMW 801. The mechanic identifies the problem, submits a parts request. The part arrives from a depot near Stuttgart, but it was manufactured at BMW's facility in Eisenach, not Allach. The bore diameter is off by a fraction. The mechanic files, tests, adjusts. He is good. He is experienced. He has been doing this for 2 years. But he is one man, and there are 11 aircraft on this field waiting for the same kind of work. And 2 of the other mechanics were transferred to the Eastern Front last month, and the replacement who arrived yesterday was a 19-year-old conscript from a bakery in Saxony who has never seen the inside of a radial engine. The Focke-Wulf sits for 4 days. When it finally flies again, the pilot who takes it up has 47 hours of total flight time. 6 months earlier, a Luftwaffe fighter pilot entered combat with over 200 hours. But experienced pilots were dying faster than they could be replaced, and experienced mechanics were disappearing almost as fast, pulled to the front, killed in bombing raids, or simply worked to exhaustion. The Americans had a name for what they were doing, though most of them didn't think of it in strategic terms. They called it maintenance by replacement. Break apart, swap apart. The part doesn't care where it came from. The mechanic doesn't need to be an artist. The system absorbs damage and keeps moving. Germany had no name for what was happening to it, but the effect was visible to anyone who tracked the numbers. Every month, the operational strength of the Luftwaffe's fighter force shrank. Not because Germany was building fewer aircraft, but because it could not keep the ones it had in the air. Speer's factories were producing record numbers of Focke-Wulfs and Messerschmitts. They rolled off the lines in Marienburg and Regensburg and Leipzig. They were delivered to Jagdgeschwader across occupied Europe, and within weeks, a third of them were sitting on the ground with open cowlings and missing parts, waiting for hands that knew how to make them whole. Meanwhile, the Americans were converting their losses into lessons. Every B-17 that came home damaged carried data: which components failed, which took hits, which could be redesigned for faster replacement. That data flowed back to Wright, to Studebaker, to Boeing, and within weeks, the production line adjusted. A reinforced oil line here, a simplified bracket there. Not revolutionary changes, incremental ones, but each change made the next repair faster, the next turnaround shorter, the next mission possible 1 day sooner. The Germans had brilliant engineers who could design a masterpiece. The Americans had a system that could learn. And at Rechlin, in November of 1943, that system was about to reveal another layer, because a second captured American aircraft had just arrived. A single-engine fighter, enormous for its type, with an engine nearly twice the size of the Wright Cyclone. And the data plate on that engine carried a name that would disturb the Rechlin engineers even more than Studebaker had. On November 14, 1943, a Republic P-47D Thunderbolt with the nickname Beetle painted on its cowling arrived at Rechlin on a flatbed truck. It had been captured intact 3 weeks earlier when its pilot, Lieutenant William Roach of the 358th Fighter Squadron, mistook a German-controlled airfield near Caen for one in southern England and landed without a shot being fired. The aircraft was repainted in Luftwaffe markings, given a test code, and shipped east. Lerche had been waiting for this one. German pilots had been fighting Thunderbolts for months, and the reports were contradictory. At low altitude, the P-47 was heavy, sluggish in a turn, easy to outmaneuver in a Messerschmitt or a Focke-Wulf. Some pilots dismissed it. But above 20,000 feet, the reports changed. The Thunderbolt was fast. It dove like nothing the Luftwaffe had ever encountered, nearly vertical, accelerating to speeds that would tear the wings off a 109. And it absorbed punishment that should have killed it. Pilots reported putting cannon rounds into the engine cowling and watching the Thunderbolt fly home. Lerche climbed into the cockpit and spent 90 minutes in the air. He confirmed the low-altitude sluggishness. He confirmed the extraordinary dive performance. But what struck him most was not how the aircraft flew. It was what he felt through the throttle. The deep, steady, overwhelming power of the engine at altitude, where the turbo supercharger fed compressed air into an 18-cylinder radial that simply refused to lose thrust. The Pratt & Whitney R2800 Double Wasp, 2,000 horsepower, 46 liters of displacement. The most powerful single-engine fighter power plant in operational service anywhere in the world. When the Rechlin engine specialists removed the cowling from Beetle's R2800, they found exactly what they had found on the Wright Cyclone a month earlier. The same machining consistency, the same absence of hand fitting, the same uncanny uniformity between components. 18 cylinders in 2 rows, and every one identical to every other. Valve assemblies that could be swapped between cylinders without adjustment. Bearing surfaces that matched specification to within tolerances the German engineers had to measure twice to believe. And the data plate did not say Pratt & Whitney. It said Ford Motor Company, Dearborn, Michigan. Not Studebaker this time. Ford. The company that had invented the moving assembly line. The company that had once produced a Model T every 24 seconds. The company that was, at that very moment, building B-24 Liberator bombers at its Willow Run plant at a rate of 1 finished aircraft every 63 minutes. Ford was building 2,000 horsepower fighter engines on the same principles it used to build automobiles. And the engines were perfect. Keep both names in your mind now. Studebaker building 1,200 horsepower bomber engines, Ford building 2,000 horsepower fighter engines. And understand what those two names meant to an engineer at Rechlin, who spent his days surrounded by BMW 801s, assembled by concentration camp prisoners under fluorescent lights. It meant America's automobile industry was its Air Force, not its aircraft companies. Curtiss, Republic, Boeing, Consolidated. Those companies design the airplanes. But the engines inside them, the components that actually generated the power, the parts that had to be manufactured to the tightest tolerances, those were coming off production lines that had spent decades building something else entirely. The knowledge wasn't new. The machines weren't new. The workforce didn't need to be reinvented. America simply redirected an industrial capacity that already existed, that was already built on interchangeability, that already knew how to hold a 10,000th of an inch tolerance across 1 million units. Germany could not do this. Not because its automobile companies were incapable. Daimler-Benz built the DB605 engine that powered the Messerschmitt 109, and it was a superb piece of engineering. But Daimler-Benz built it the German way: skilled hands, matched tolerances, individual fitting. When Speer tried to expand production, he couldn't simply hand the blueprints to Opel or Auto Union and say, "Build this." The blueprints were not enough. The German system required the culture, the Facharbeiter, the Meister, the years of institutional knowledge embedded in the hands of men who were now dying in Russia or buried under rubble in Hamburg. The American system required the blueprints and the gauges. Give those to any factory with precision machine tools and a quality control process, and that factory could build aircraft engines. Studebaker proved it, Ford proved it, Buick proved it, Packard proved it, Dodge proved it. By the end of the war, America's automobile industry had produced over 800,000 aircraft engines. Not airframes, engines. The most complex, most precision-critical component of every aircraft in the Allied arsenal. And every part from every factory fit every other part from every other factory. Lurka never wrote explicitly about this industrial revelation in his memoir. He was a pilot, not an economist. But he wrote something about the Thunderbolt that carried the weight of everything his colleagues in the engine shop were discovering. He called it a practical aircraft. Not crude, not primitive, not inferior. Practical. Built to fight, built to survive, built to be fixed, built to fly again. Built by a nation that understood something Germany did not. What that understanding would look like on the battlefield, what it would cost the Luftwaffe in blood, was already becoming visible in the skies over the Reich. In January of 1944, the 8th Air Force introduced the P-51B Mustang as a long-range escort fighter over Germany. Its engine was a Packard V1650, a Rolls-Royce Merlin built under license by the Packard Motor Car Company of Detroit. Another automobile manufacturer. Another set of blueprints handed to a factory that had been building luxury sedans, and within months was producing one of the finest liquid-cooled aircraft engines in the world. To tolerances so tight that Rolls-Royce engineers who inspected the Packard-built Merlins reportedly said they were finished to a higher standard than the British originals. The Mustang changed the air war. For the first time, American fighters could escort bombers all the way to Berlin and back. Luftwaffe interceptors that had operated with relative freedom beyond the range of P-47s and Spitfires now found Mustangs waiting for them at 30,000 feet. The killing began to reverse direction. But pay attention to what made that reversal possible, because it was not the Mustang alone. It was the fact that America could build the Mustang, and its engine, and its drop tanks, and its spare parts, and deliver them across an ocean in quantities that absorbed losses and kept growing. When a Mustang went down over Magdeburg, and hundreds did, another Mustang was already on a ship. When its Packard Merlin took a 20mm shell through the coolant system, and the pilot belly landed in a Belgian field, a replacement engine was already in a crate at the depot. Same tolerances, same specifications, same fit. The pilot who walked away from that landing was back in a cockpit within a week. Not because he was braver than a German pilot, but because the machine that carried him was part of a system that could regenerate itself faster than the enemy could damage it. Germany could not regenerate. It could only bleed. By the spring of 1944, Luftwaffe fighter losses had reached a rate that no amount of industrial effort could reverse. In February and March alone, a period the Americans called Big Week, the 8th and 15th Air Forces launched coordinated raids against aircraft factories across the Reich. The targets were not chosen at random. They struck at the production chain itself. Messerschmitt plants in Augsburg and Regensburg, Focke-Wulf plants in Oschersleben and Marienburg, the ball bearing works at Schweinfurt that supplied every engine factory in Germany. Speer's organization dispersed production into smaller facilities, forest clearings, highway tunnels, salt mines. It was brilliant improvisation. Output recovered faster than the Allies expected. But dispersal created a new problem that interchangeability would have solved and that hand-fitting could not. When components were manufactured in a dozen scattered workshops instead of one centralized plant, the variations between them increased. A crankcase machined in a tunnel near Nordhausen did not mate cleanly with cylinder assemblies produced in a workshop outside Kassel. The Facharbeiter who might have reconciled the difference was dead, or on the Eastern Front, or had been replaced by a forced laborer who could not read the engineering drawings. The aircraft came off the line. But they came off wrong, slightly, invisibly, fatally wrong. Engines that overheated, transmissions that seized, hydraulics that leaked. The readiness rates told the story. In some Jagdgeschwader, operational availability dropped below 40%. Brand new aircraft sat on fields across the Reich, grounded not by enemy action, but by parts that did not fit, by repairs that could not be completed, by a maintenance system that had been designed for peacetime production and was now drowning in wartime volume. And every month, the pilot who finally climbed into one of those repaired fighters had less training than the pilot before him. In 1942, a Luftwaffe fighter pilot entered combat with over 200 hours of flight time. By the summer of '44, that number had fallen below 80. Some pilots arrived at their units with fewer than 50. They were brave. Many of them were volunteers. They climbed into aircraft they barely knew how to fly, took off to meet formations of American bombers escorted by American fighters flown by pilots with 300 hours of training, and they died. Not because they were worse men, because the system behind them was breaking, and the system behind their enemy was not. That was the final layer of what the engineers at Rechlin had uncovered in October 1943, the layer that no technical report could fully articulate, the layer that went beyond metallurgy and tolerances and production numbers into something closer to a national philosophy. The German way of building things was a mirror of the German way of waging war, masterful, concentrated, dependent on extraordinary individuals performing at the peak of their skill. When those individuals were present, the Experten in the cockpit, the Facharbeiter on the factory floor, the system produced results that no one in the world could match. A single Tiger tank could destroy 10 Shermans. A single FW-190 in the hands of a veteran could scatter a squadron. But the war did not ask for single performances. It asked for 10,000 performances, 100,000, a million, day after day, month after month, in every weather, across every front, with whatever hands were available. And for that kind of war, the German system had no answer. The American system did. It was built into every Wright Cyclone that rolled off Studebaker's line in South Bend, every double Wasp that came out of Ford's Rouge plant, every Packard Merlin destined for a Mustang. The answer was not genius, it was not craftsmanship, it was not even technology. It was a bet, placed 140 years before the war began, that a machine could be trusted more than a hand. Hans Werner Lerche flew his last mission in April of 1945, a Dornier 335, the fastest piston-engine aircraft Germany ever produced, racing west at low altitude as the Soviet Army closed on Rechlin from the east. He landed at a field in Schleswig-Holstein and surrendered to British forces. He had flown 125 aircraft types in his career without crashing a single one. He was 31 years old. In the years after the war, Lerche returned to engineering. He lived quietly in West Germany, worked in the aviation industry, and in 1977, standing in front of a restored Dornier 335 at the Deutsches Museum in Munich, he decided to write his memoir. The book appeared in English 3 years later, under the title Luftwaffe Test Pilot. In it, he described the captured B-17 with professional admiration, its supercharged engines, its ability to fly on 3 of 4, the steadiness of its controls under load. He called the Thunderbolt a practical aircraft, its power at altitude unlike anything he had experienced in a German cockpit. He did not sentimentalize. He did not editorialize. He stated what he had felt through the stick and the throttle, and he let the reader understand the rest. He never wrote about the data plates. He never wrote about Studebaker or Ford. Perhaps he didn't know. Perhaps he did and chose not to say. A pilot looks at an engine from one direction. The men who disassembled those engines on the Rechlin workshop floor looked from another. But both directions led to the same place. Rechlin itself did not survive the war. In the final days of April 45, retreating German units destroyed what they could. Soviet forces took the airfield on the 2nd of May. The workshops where those American engines had been measured and catalogued were stripped, and most of the technical reports were lost or scattered. The hexagonal ring road that once bounded the Luftwaffe's greatest test facility is still there, enclosing 500 acres of meadow where a music festival is held each summer. The buildings are mostly gone. A small aviation museum stands on the north side. Among its exhibits, there is no Wright Cyclone, no Pratt & Whitney Double Wasp, no data plate reading Studebaker Corporation, South Bend, Indiana. But the evidence didn't need to survive in a museum, because it had already survived in the outcome. By the end of the war, the United States had produced over 800,000 aircraft engines. Automobile companies, Studebaker, Ford, Packard, Buick, Dodge, Chevrolet, Chrysler, had built the majority of them. Those engines powered the bombers that broke German industry, the fighters that broke the Luftwaffe, the transports that sustained the invasion of Europe. Not one of those companies had built an aircraft engine before the war. All of them produced engines to tolerances so exact that any part from any factory fit any other engine of the same type in any theater on any airfield without adjustment. Germany produced its engines with masterwork and ran out of masters. America produced its engines with a system and never ran out of factories. Lerche died in 1980, 1 year before his English memoir was published. He never became famous. He is not a name most people know. But he sat in the cockpits of America's best machines, felt their power, and understood, with the quiet clarity of an engineer who had spent his life testing the limits of what metal and fuel and human design could achieve, that what he was touching was not merely an airplane. It was the output of an entire civilization that had decided, a long time ago, that the right way to build something was to build it so that anyone, anywhere, could fix it. That was what happened when the Germans opened an American engine for the first time. They expected to find a machine. They found a philosophy. And by the time they understood what it meant, the sky was already full of its consequences. Thank you for staying with this story to the end. If it gave you something, a fact you didn't know, a way of seeing this war that you hadn't considered, a like goes a long way. It tells the algorithm that this kind of history matters, and it helps these stories reach the people who care about them most. If you're not subscribed yet, now is the time. Hit subscribe and the bell so you don't miss what's coming next. I'd love to hear from you in the comments. Where are you watching from today? And if someone in your family served in the Second World War, your father, your grandfather, your uncle, tell us about them. Every story matters. Every name deserves to be remembered. Thank you. I'll see you in the next one.